Hello and welcome. These are a series of lectures intended for students at Oregon State University for the course Math 665. In this class, we'll be talking about Markov processes and applications of Bayesian inference. This first series of lectures are intended as a probability review. They're based on the first chapter, inspired by the first chapter of stochastic processes with R. Here we have the textbook right here, Introduction to Stochastic Processes with R by DeBraw. You can find the book on the campus library online, and it's accessible through the website, and you can follow along there. The lectures, like I said, are going to be inspired by this textbook. I'm trying to cover all the content that's there, but at the same time, I'm not necessarily following the textbook. What I'm doing is I'm trying to just interpret the topics as I see them and give you another perspective. And this is supposed to be an additional resource to a textbook, and I'm going to move fairly quickly through these topics as I suspect that many of you have seen some of these topics before. This is just really intended as a review and just kind of get everyone on the same page. For the first lecture today, we're going to talk about just the foundation of probability theory, the probability spaces, and we're just going to focus on the very basics. And the punchline of this whole lecture is that to actually work on probability, you need a probability function. And that's going to be the main object that we work with. And probability theory can be very nuanced and fairly abstract, but the point here for this course is that we're going to be pragmatic about probability theory, and we're not going to go in the weeds and try to go at the very fine details. We're just working with probability functions, and we're going to avoid any nasty issues in this class. So we're going to just be pragmatic and just work with probability functions. So let me just start with the basics. And in this first lectures, I'll set up the axiomatic definition of a probability space, but at the end, I want to get to the important objects that we will be using. And some of this stuff is just for details, for make sure that everything is well defined, and it's a very powerful theory, but we don't need everything in such fine details. We just need something to work with. But let me start with this definition for a probability space. And when we think of a probability space, this is really just a triplet. It's the information given by these three objects. The first object, omega, is the outcome space. This is all the possible outcomes of a random experiment or an experiment or some set of outcomes of something that may happen. And with this, with all the possible outcomes, we also are going to add this set, which I call B in here, which is the set of possible events. And in here for now, the way that we want to think about it and the way that we see it here in this picture, this omega we have, this is going to be our universe. This is the set of all outcomes. And in here, the events, the way that we want to think about them initially, is going to be that possible events are subsets of the universe. And the third object that we want for a probability space is a probability function. And this is going to tell us, it's going to be a map from the events to the interval 0 or 1. Probability is a number between 0 and 1, and the probability function is going to map our events, which are going to be subsets, to a number between 0 and 1. And this is what I've depicted here. This is the basic definition of probability space. I'll give more information on this set of possible events, and this is where the subtlety of a probability space comes in. But we will be able to avoid such a subtlety. So let's move on and talk more about this set of possible events, set of events. This B, if this collection of subsets of omega of this, which is the set of events, we actually require this to be a sigma field, and this sigma field satisfies this following conditions: 1, 3, and 4. What happened to 2? Oh, found it. Here's 2. So in here, the first condition is that the empty set is in the collection of events. And this is just axiomatically, really the interpretation is that there's a possibility that nothing may happen. And this is going to mean that the empty set has to be in this set of events. And additionally, if you have an event in the set of events, then you're required to have the complement of that event, meaning that if something is possible to happen, then it's also possible for the opposite to happen. So we have these two conditions, and then we have two more conditions. And here, if you have a collection of events, EK, indexed with the natural numbers, this means that the union of all these events is also in B, this set of events. And really this means if event 1 could happen and event 2 could happen, they're both in B, then event 1 or event 2 may happen. So if one of these two events is possible, then their union is also possible, so either or. So this is also going to be a possibility of events. And then similarly, if you have that an event 1 could happen and an event 2 could happen, then you can build another event, which is the intersection, meaning that event 1 and event 2 will happen. And that's the fourth and last requirement for a sigma field. And as I mentioned earlier, B is the set of all possible events in our probability space, and this must be a sigma field. So part of the requirement for a probability space is that the set of events is a sigma field, and this is a consistency check. And additionally, we have, and this is where things can get really, really crazy, and this is where how probability theory got rigorous, because initially this idea of a sigma field didn't exist, but there were some contradictions arising, and in particular, if you look at the Banach-Tarski paradox, which I think this is definitely not the spelling of Banach-Tarski. So let's see it real quick. Banach-Tarski. Banach-Tarski. There we go. We have the correct spelling. This is the Banach-Tarski topology. Um, so let's see if we see it. Hormone treatment. So let's see right here. Given a solid ball in three-dimensional space, there exists a decomposition of balls into a finite number of disjoint subsets, which can then be put back together in a different way to yield two identical copies of the original ball. So essentially, you can see it here in this picture. You can decompose the ball into different pieces and then glue them together to get two copies of the ball. And this is what happens when you have an infinite number of elements, an uncountably infinite number of elements in your outcome space. If all the sets are possible as events, then you may be in the situation where you can decompose your your universe into two universes, and then you get that 1 is equal to 1 plus 1. So one of the ways to be consistent and avoid this type of issues is to work with sigma fields. But again, this is getting into the weeds of the theory, and in most practical cases, we're going to have, in this course, we're going to have that, in all cases, we're going to have that omega, the outcome space is countable. And in that case, we can just think of our sigma field to be the set of all subsets of omega. And in this case, it's going to be fine. And as I mentioned above, it's when omega is uncountable that you can run into the possible. I should have known that's the Banach. Let's see, did I spell it right? Banach, yeah. So when omega is uncountable, that's when you can run into possible paradoxes. But in this case, in this course, we're not gonna worry too much about sigma fields. This is just gonna be, this is something in the theory that we should kind of have in the back of our heads, but in most practical terms, it's not going to affect anything we do. I just like to include a short and brief discussion about this so you're aware about it, but practically it's not going to affect us. So for omega being countable, we can take the sigma field to be the set of all subsets of omega. Now, for the uncountable case, the case that we'll consider most often is the real numbers, where our outcome space will be the real numbers. And in this case, we typically have what we call the Borel sigma field. And this is a sigma field created so that we don't have this Banach-Tarski paradox, so that everything is consistent. And in here, the Borel sigma field is generated. We say that it's generated by open sets. And in particular, what we mean by this is that we require all open sets to be in the Borel sigma field. So this is the notation for the Borel sigma field. And then using these 4 axioms or 4 conditions, we say that any other set created using these 4 conditions is also in the Borel sigma field. And for instance, if we have the empty set, this is going to be an open set. Then we can take the complement of that. This is using the first axiom. We have this is true. And then by the second axiom, or condition rather, we have that this is also true. And we see that by having this in the Borel sigma field, we additionally have R to be in the sigma field. And then we can use the rest of the axioms to construct other sets to be in the Borel sigma field. And in here, we can actually construct a closed set. And the way we do this is that we take the complement of this open set and do the intersection with the complement of this other open set. And we have the complements are going to be given by this, and this one by this, and then we take the intersection of this, and if we require that A is less than B, then we have that this is in the Borel sigma field. So by just requiring the open sets to be in the Borel sigma field, we can start constructing other sets using these conditions. And the Borel sigma field is the unique sigma field generated by this open sets in a precise way. And here, using the condition that unions are in the Borel sigma field, we have that disconnected open intervals are also in there. And this is the way that you want to think about Borel sigma field. Just events that can be generated, created using the four conditions by open sets. Now, we've talked about the Borel sigma field, and we have for the probability space, and in the probability space we also have the outcome space, omega, our universe, and that could literally be anything. It's just any set. And then the third object that we have is the probability function. The probability function as the Borel sigma field the Borel sigma field has to satisfy certain conditions, and for it to make sense with probability, we have this following two conditions. One is that the probability of the event omega is that something happens, that anything happens, has to be equal to 1, because something must always happen. So this is going to be one of the conditions that the probability function has to satisfy. And the second condition that the probability function has to satisfy is countable additivity. And here we have a union of events EI that are pairwise disjoint, and countable additivity tells us that the probability of the union is the sum of the probabilities. And in here, I have a short example where I use this countable additivity. It's very handy and comes up a lot, and it's a basis of the probability theory. So for instance, in here, I'm going to derive the complement formula, and I have an event E in B, and I can write omega as the union of E and its complement. Then by the first property, we have that 1 is the probability of omega. I can write omega as E union E complement. And then by countable additivity, I can write a sum of E and E complement. And then now solving for the probability of E complement, I have the complement formula. So probability of E complement is always equal to 1 minus probability of E. All right, so this is the very basic foundation of probability theory, this probability space which has three objects, the outcome space, omega, which could be literally anything, any set. We have a sigma field, which is the set of all the events, and this needs to be a sigma field. And then lastly, we have a probability function, which has to satisfy this countable additivity and that the probability of the outcome space is equal to 1. So let's do a quick short example of a probability function and a probability space. And again, to define a probability space, we need three objects. the outcome space, the sigma field, and the probability function. And again, if we have a discrete outcome space, it's safe to assume that the sigma field is just going to be all subsets of omega. And there's no harm in that. It's whenever omega is uncountable that you need a little bit more care, but in all the cases that we will consider later when omega is uncountable, which is going to be the real numbers, when omega is equal to the real numbers, then we know to use the Borel sigma field. But in any case, we have three objects to define a probability space, and a typical probability function is the counting probability function. And here, the counting probability function just tells us that the probability of an event is the cardinality of the set E divided by N. Alternatively, you can think of, instead of N, you can just say the cardinality of omega. And this is a counting probability because you just determine the probability by just counting the number of elements. And this is the most basic and the most natural probability function. And here we have two examples. Fair coin. The possible outcomes that you have is either heads or tails. And to compute the probability of heads, you think of this heads just as an event H, and you count the number of elements in this event, divide by 2, and you have 1/2. And so this is a fair coin. And we have a die, a 6-sided die, where the outcome space is now 1, 2, 3, 4, 5, 6. And now I'm creating a different event rather than just a specific number. I could say something like, what's the event that when I roll a die, I get an even number? And to compute the probability, I just use the counting probability, which is the number of elements in E. And here, E really is going to be the set 2, 4, 6. So I count 1, 2, 3, and I get this 3, and then I divide by 6, and I get 1/2. And I compute probability this way. So this does it for today, or for this lecture rather. And we'll talk about random variables in the next lecture. And in this lecture, I just wanted to set up what is a probability space. And moreover, what I want to get across in this lecture is that we have these three objects to define the probability space. Omega it's most likely going to be in all our examples that we're going to work with. It's going to be given. It's going to be easily deduced from context, and it's typically going to be the integers or the real numbers. It's not going to be something too crazy, or it could be, but really in the background it could be something fairly abstract. But we just need to think of these two specific cases: the integers, finite sets, or the real numbers. And then, so this is going to be something that's given to you, and it's easy to understand. And then you have two more things, the sigma field and the probability function. And what I want to say, my point throughout this whole lecture is that in this class, we don't need to worry about the sigma field. This is something that we're just going to put to the back of our heads and not worry about it. And then what this means is that in our study of probability in this course, what it really depends on is the probability function. So this is going to be the main objects of study. And this is going to be the center stage of this class, and we're going to try to figure out how to compute the probability functions. And it's going to be, in practical terms, this is what we want to determine, the probability function. And we'll see more examples in the following lectures. And But for now, what we want to think about is the probability function. Okay, this is it. We'll continue on the next lecture with random variables.